Welcome to Astrophiz. I'm Brendan O'Brien, and we acknowledge the traditional owners of this land and their ancient astronomical heritage. Join us as we fight for a greener future and sit down with the world's leading space scientists to see how our universe works. And right now, you are invited to join me as we zoom over 8 time zones to ESA, the European Space Agency, to speak with the absolutely wonderful Dr. Gabriela Ligeza, who literally guides the ExoMars Rosalind Franklin Rover on its mission to find evidence of life on Mars. She is truly amazing. Enjoy. Hello, Gabriela.
Hi, Brendan. Hi.
And hello, listeners. While the world watches the stars, our wonderful guest today is focused on the dirt beneath the wheels of the next generation of Mars explorers. Joining us from the European Space Agency in the Netherlands, Dr. Gabriela Ligeza is an internal research fellow working at the cutting edge of Mars exploration, from developing science sampling strategies for the ExoMars rover to scouting landing sites for the Artemis 3 mission. Her work is the bridge between the maps we draw from orbit and the physical reality of planetary surfaces. Gabriela, it's a genuine privilege to have you here on the show.
Thank you very much, Brendan, for this wonderful introduction. And thank you very much for inviting me to be on your podcast today. It's a great pleasure.
It's a real pleasure. It's all mine. Thank you. Now, before we cast our eyes upwards to your incredible work on lunar and Martian missions, I'd love to ground ourselves with your own story. Could you share with us a little about your family, where you grew up in Poland and where you spent your formative years? And perhaps you could tell us about the spark that first ignited your passions for science.
Sure. So I grew up in a small village, actually, in the south of Poland, close to Krakow. I think this is the easiest to put it on the map. And I spent my first 18 years there up until high school. And then I follow up with my bachelor's degree at university in Wales. And I then went for exchange to Canada. Then I came back to Wales. I started my master's in Zurich, followed my PhD in Basel. So it was a bit international. I moved a lot when I was studying. When the spark for science started. So actually, I was a very curious child and I was very interested in exploring the world. So, I was fascinated by glaciers, volcanoes, and I always wanted to find out all about the system of the planet Earth, how it's all connected to bring the life here on Earth. So my first fascination to science came up actually from our own planet. And when I was growing up, I told my parents I wanted to be explorer and travel the world. But for space specifically, I remember the first moment, and it came directly actually from the traveling first. So I couldn't wait to travel and explore. So I signed for a post-crossing. I'm not sure if you ever heard about it. It's a system where you send one postcard to random place in the world and you receive one back in return. So I received a lot of postcards from people all around the world about beautiful nature. But there was one postcard that really blew my mind, and it was sent to me by NASA employee from Kennedy Space Center in Florida. And it showed the Earth from space, a famous blue marble picture. And this is exactly when I had this aha moment. And I was thinking, wow, working for a space agency must be the coolest job on the planet. But at the time, of course, I didn't know how to do it. I really come from a small family, from small village. My parents never went to university themselves. So it was more like a dream to work for a space agency. So I stuck to the science and exploration, and I decided to keep pursuing my degree in earth sciences. And I thought that maybe one day, I will find my way to space. So my first interest in science and space was before high school, and it comes from interest in geology.
Beautiful. Thank you. I can imagine you telling your parents that you wanted to be an explorer, and you've done more than that. You've explored more than the Earth. You're actually at the forefront of exploring our solar system. Now, just before we get into the complexities of mission planning at ESA, let's also go back to the early days, your launch phase. As you mentioned, you've studied in Poland, in Wales, in Canada, in Switzerland. Was there a specific moment during those early studies, perhaps at Aberystwyth, or perhaps when you went to Ottawa in Canada? When did you realise that your future wasn't limited to earth sciences, but actually in planetary sciences?
That's a good question. And that wasn't happening until the end of my master's degree at ETH Zurich. So it came up quite late, this realization. There was a public lecture at ETH where they invited NASA employees and astronauts to give a public talk. And I was absolutely blown away to hear NASA science administrator explaining the future upcoming missions to the moon, Mars, and beyond. And I was also very mesmerized by all astronauts who have been to either International Space Station or who had a chance to work on the moon as well. And it was a very special day for me, I remember. And also because during that day, I have discovered that this postcard I have received as a child was actually taken by an astronaut who was a geologist on his way to the moon. So on that day, on doing this talk, I Googled, can a geologist work for space agency? And this is how I found out it was a real possibility. So I browsed multiple websites and I found out that the European Space Agency back in time was looking for interns with a geology background, specifically with someone with mineralogy and geochemistry specialization. And that was exactly my specialization at ETH, who would help them to create the mineralogical database for future human missions to Mars and Moon, and who would also help them to contribute with astronaut training during the 6 months period. So this is exactly how I found out that geologists can work for space agency. And actually they were looking for people with my skills, with science background, with mineralogy and geochemistry expertise. So that was the moment. Also, I applied right away and I was lucky to get that position. So this was the time and moment that changed my course of life from earth sciences to space sciences.
Fantastic. What a stellar track record. I've had a really good look at your CV. It is sensational. What really stands out is that while you were tackling your PhD at the University of Basel, you were also navigating the real world as, I shouldn't say that, as a project manager and an analyst. Now, often we think of academia and industry as two separate worlds, but for the students listening, how did having one foot in the industry door change the way you look at scientific research?
I think working industry before my PhD really changed the way how I looked at the research later on. So at Swiss Space Center, where I worked as a project manager, I got a broad overview of space sector about the technologies, trends, and the real challenges that the space industry was facing. So then when I was about to choose the topic of my PhD, I wasn't only thinking about the scientific curiosity, but I also wanted to work on the project that would have a practical impact. So that was a very good start, to start from the industry, find out what is out there, what is interesting, to find a topic that it's good for me and for my personal interest and for my career growth, as well as the practical impact. It also taught me other skills. For example, how to set realistic goals and managing timelines, and how to make my PhD goal-oriented, because, we have a short timeline, we have 4 years. So project management taught me how to complete this meaningful project, deliver meaningful results on time. And honestly, I think both academia and industry require a lot of flexibility and adaptability from us. So I think having this experience in both worlds was a huge advantage. And also, this is what I would recommend to young people who don't know what are the strengths are, to try both of these words, either from internships or short job, before you make committed decision to PhD, to find out what actually are your strengths, what you like, and how you can apply diverse set of skills either to academia or industry, because these words, they really overlap, and I think they are enriching how you are approaching your research later on.
Thank you, Gabriela. That is a powerful perspective for any aspiring researcher listening to you right now. Now, just before we have a deeper look at your PhD, I found your thesis online and I loved reading your paper. Look, to be fair, I really only fully understood your abstract and your conclusion, but I really loved the acknowledgement section where you thanked your supervisors, your colleagues, your fellow PhDs and researchers, your parents, your grandmother, and your brother Shamak, and some furry friends like Ziggy and Ollie and Riley. I may get to introduce you to our Ashie at the end of this interview. She's a beautiful cat. She's 20 years old and beautiful. She sleeps most of the time, which is quite an inspiration, but we probably get back to the science, please. So, looking specifically at your doctoral work at the University of Basel, your thesis was a deep dive into the imaging and operational strategies that we need for planetary surface exploration. It's becoming a huge thing right now as we speak. You spent a significant amount of time in the Mars lab simulating those tricky Martian lighting conditions. Now, for our listeners who might picture a space camera as a simple point and shoot or something on your phone, what was the most surprising thing that you discovered about how light and shadow can either reveal or completely hide the geological history of a rock visually?
Okay, thank you, Brendan. First of all, thank you for reading my acknowledgement section in such a detail. I had a great laugh about everything you mentioned. There were a lot of people who contributed to the success, and I'm very curious to find out about Ashi later on. But regarding my PhD thesis, I worked, as you mentioned, on operational strategies for one of the instruments on board ESA's ExoMars Rosalind Franklin rover called CLUPI, which is a close-up imager designed to acquire detailed images of rocks, outcrops, and drill samples on Mars. And it's installed on top of the drill box of the rover, so it has multiple points of view and fields of view. It's designed to capture geological samples of the Martian surface. And my research was focused on simulating realistic operational lighting conditions under different lighting environments on Mars in Mars Labor. So it was an indoor facility at the University of Basel, which was designed to replicate these lighting conditions. You might know that unlike on Earth, light on Mars is much more diffused because we have a fine dust suspended in the atmosphere. And this creates softer shadows, but also changes the way how textures, colors, and surface details appear in the images. Also, Mars has a very unique optical conditions. So, for example, during the sunrise and sunset, the sky can appear bluish around the sun, while the rest of the atmosphere has reddish tones. due to the iron dust scattering light differently than on Earth. So I was exactly simulating these conditions to see how the human eye can interpret different textures and colors and minerals in these different light as well conditions. And one of the most surprising things which I have realized is that the exact same rock can tell you completely different story depending on the time of the day, how you acquire picture, the angle, how you approach the rock with the camera, also how you position camera in regards to the rock. And like that, the one rock can tell different story based on how you are acquiring this image. So we found out that the low angle light can enhance the topography and make textures, layering, and some other sedimentary features to suddenly pop up and maximize the scientific information, while the diffuse light can hide sometimes these features sometimes, but in other cases can also, in contrast, reveal subtle minerally textures and shadows that shadows otherwise would make them obscure. So this is important because, as you know, and probably listeners as well, when we go to explore surfaces on Mars, we don't have room for mistakes, and we can take 1 or 2 images per day that we can send back to Earth. So we have to make sure that the scientific information is recorded in these images, the way that scientists can do follow-up investigation with other instruments based on that image. And yes, and the data that is sent back delivers meaningful results to us. So in planetary geology, working with the light is not just about taking a beautiful picture, but it directly affects whether we correctly interpret the geological history of rock or if we completely miss the important evidence.
Beautiful. And it looks like you're solving a lot of the problems even long before the rovers go to Mars and the instruments have to go to work. But it also sounds like to me that there will also likely be problems that arise up there, but you're very well placed to solve problems as you go. Thank you so much. Well, we've got the backstory loaded and we've got that on board. Let's do a little more sciencing now. Can we talk about your current mission at the European Space Agency? You're working on the science sampling strategy for the ExoMars rover. Can you explain the high stakes puzzle that you're solving here, and how do you decide which Martian rocks are the right ones to sample when you're 225 million kilometres away? How are you going to make those decisions?
Yeah, correct. So it's an interdisciplinary project that I'm currently working on, and it consists of 2 main parts. So the science sampling strategy has 2 main parts. So the first one is based on geology and the remote sensing. So we have a lot of data. We have a geological map and we have data images from Mars, but also the mineralogical information from instruments like, for example, microomega, that give us idea what can we find in this region where we land that calls Oxia Planum. So based on the combination of these factors, I review the geology and locate the most promising environments for past life on Mars. So I'm focusing mostly on these geological paleoenvironmental hotspots that could not only host the life before, but also they could have preserved them over like long period of time. So for example, we are particularly interested in iron magnesium phyllosilicates that have been detected mineralogically from the orbit, because these minerals, they are known to be formed in the presence of water, and they have a high potential to preserve these biosignatures over the long period of time. But we also identified several regions, for example, that these clays are heavily fractured. So everywhere in Oxia, you see these long and wide space fractures from the orbit. That also requires some follow-up investigation with the rover, because we would like to look for any possible sign of mineralization. So any fluid that could come up and build up within these fractures could also preserve these biomolecules and biosignatures. And for example, another type of hotspot environment, which we are looking to investigate further, is the hydrated silica. Some of the signal was detected from the orbit as well. And there are some albedo differences that we see from the remote sensing. So we have like these bright spots all over, not all over the Oxia Planum, but mostly in the middle of Oxia Planum, that we don't necessarily know yet the composition yet, but we make some preliminary interpretation because for the mineralogy that cannot be resolved from the orbit, that it could contain some signature of hydrated silica that has been found, for example, before in situ with Spirit rover, past rover mission on Mars. And it also is indicator of past hydrothermal environments from which the life originates itself. So yes, we are looking for the geology and these mineralogical clues that give us some, it's like in exploration for mineral resources. You are in Australia, so you are looking for these signatures, for these proxies that we can later on pinpoint and investigate further with much more sophisticated instruments that they are on board of ExoMars Rosalind Franklin rover. And that's exactly the second part of my work. So the second part is more operational. So it's putting all of this science into operations. And it aims to develop operational strategy for the rover, how to identify these features that I mentioned before. So we are defining how the rover and its instruments should investigate those targets under very limited mission resources, such as power, data volume, and thermal constraints in daily operations. And in that project, I identify minimum sets of observation for each of these instruments, which they must acquire to confidently characterize this feature, to assess the potential of its habitability and biosignature preservation. So for that second part of the project, I work with PIs, principal investigators of each of these instruments, and we are developing science traceability matrices for each of these instruments. So the moment that we are on the surface operations, we know the capability of these instruments, each of them, to solve these big questions regarding the habitability of the interesting targets.
Fantastic. Thanks, Gabriela. Now, one of the big unanswered questions, you mentioned morphological biosignatures, and one of the big questions that we have in science is, are we alone? And your work is on the cutting edge of looking for the possibility that life is or once was present on the red planet. Now, I went back and I found one of your papers from last year that lists some of those morphological biosignatures that can be found in Martian rocks. Can you tell our listeners what morphological biosignatures are and how can they indicate evidence of life on other planets?
So morphological biosignatures are basically tiny shapes, textures, and structures embedded in the rock that have been created by ancient microbial life. So you can think fossil fingerprints left behind in geology. On Earth, some of the oldest evidence of life, it's dating back to 3.5 billion years ago, comes from exactly these structures, which are preserved in very ancient rocks, such as, for example, stromatolites formed microbial communities. Stromatolites, for example, from Pilbara in Australia are the perfect example of this ancient microbial life imprinted in the rocks.
Yep.
However, What is very important is that we are not hunting for morphological biosignatures themselves, and we have not found them on Mars yet. But if we did, of course, it will be like a holy grail of planetary science.
Oh, yes.
But the tricky part is that Mars loves to play tricks on us, because a lot of these features, they look like they can be done by biological processes, but they can be also done purely by abiotic, so just geological processes. So our job is to play detectives. If we see something that looks like a morphological biosignature, so like laminated, wavy kind of structure of a rock, we look in depth to do follow-up investigation on this morphology to find out whether or not the mineralogy associated with this morphology could be biotic as well. And we check for the molecular composition also of this rock. Because when we speak about the biosignatures on Mars, we are talking about microbial life. So something very tiny, something we can only confirm with mass spectrometers. So the morphological biosignatures is the first step we are looking for. But then we are checking chemistry and mineralogy and biomolecules present within them.
Beautiful. Thank you, Gabriela. What a beautiful set of instruments you have to work with. Now, you've also spent some time working with the Robotic Systems Lab at ETH Zurich on the animal-legged robots. Now, I love dogs in space like anyone, and I love the MacGyver spirit of this, using four-legged robots to map the lunar resources. What can a legged robot do on the moon or Mars that a traditional wheeled rover simply cannot do?
Yeah, so legged robots are extremely exciting because they can go to places that traditional wheeled rovers simply cannot reach. So the wheeled rovers are capable, but they move, very slowly and struggle in rough terrain where we have a lot of dust, rock, and boulders. So the animal-legged robots, they have advanced sensors in their feet that they help them to assess the risk basically while they are walking on it or while they are trying to put their feet over the terrain. So they can make these intelligent decisions whether or not they walk simply over the rocks or just take a different path and choose a safer way to navigate. They also, what they can do, they can also climb steep slopes and potentially explore places such as rims of craters or lava tubes, which are also places on the moon, for example, that can host valuable resources. And we cannot get close to the crater rim or the lava tube with the wheeled rover because that is simply too dangerous. So these legged robots, they can basically give us access to places that are still unexplored on planetary surfaces. Also, what is the advantage to wheeled systems is that they move much faster than traditional rovers. So we can map and prospect for resources over large areas much quicker and get the first overview what geology we are working with instead of moving few meters per day and solving one puzzle by each. There we get a broader picture much faster. Also, in our legged robots, we worked on science autonomy. So we try not to only make the prospection faster, but also more autonomous without much of human supervision. So we train our intelligent systems robots to acquire images, take the spectroscopic data of interesting rocks that could consist of potential resources, and send them back autonomously to the mission control without much human supervision. So we believe that they can either work autonomously on Moon or Mars, or they can work in parallel with humans to expedite the exploration.
Wow, that's so exciting. Dogs in
Mhm.
space, autonomous dogs in space. You must have such an exciting day at work every day. That is fantastic. Now, way back in 2023, you were at NASA's Johnson Space Center in Houston as an intern, and you were helping to establish the geological sampling locations for the Artemis crew. What was it
Yes.
like to look at that map of the South Pole of the moon, the lunar South Pole, and realize that you were helping to decide where the first humans in over 50 years will actually step and work when Artemis 4 is scheduled to land there in 2028?
Yeah, so that was also a very important aspect of my PhD, and I call it a highlight that I also had a chance to work on the lunar geology. So you mentioned how it's to look on the maps. Actually, the first part of the project was to create a geological and mineralogical map. So we were not given a data, but we had to create data and then make these decisions. But maybe some context before I tell you how we created the different data sets. What is very interesting about lunar South Pole geology is that it's totally different geology than we have from the Apollo landing site, so past missions to the moon. So in the past, we sampled mostly basaltic terrains, which were formed by ancient volcanic activity. But in the lunar South Pole, when we are returning to the moon, we are expecting a totally different story and totally different material. So here we are hunting for rocks that they call anorthosite, and they are one of the oldest crustal rocks on the moon. So we are accessing much older rocks than with Apollo missions. So our job was to create a map, a geological map that shows where is the exposure of these outcrops with anorthosites in the lunar South Pole. So the challenge was to analyze the topography. So we also created a mineralogical maps that showed us where the signatures of anorthosite mineral was present. However, the challenge in the lunar South Pole is that this region is extremely cratered. So we have craters that are several kilometers deep, which make navigation and sampling much more difficult. Also, what we have discovered is that these ancient rocks are covered by ejecta. So, as I mentioned, this terrain is heavily cratered, so we get a lot of exposed material from these craters covering the outcrops. So, we have calculated where and how much ejecta we expect to find in different regions of lunar South Pole to help us estimate the best locations where to sample these pure materials. But also we focus on identifying, for example, areas where the ejecta from South Pole Aitken Basin, so it's the biggest basin on the moon. Also, it has some material in the lunar South Pole. We also identify where it's present to also diversify the samples for the return. And I think it was incredible feeling to realize that the maps that we were creating and the analysis which we presented could help the mission planners to decide what are the most optimal places for astronauts to go and collect these samples and bring back totally different rocks to Earth than we brought with Apollo.
Wow. That's beautiful. It's so exciting. And you were also involved in creating the ESA Pangea mineralogical database, but I'd like to now talk about how you help prepare geological and astrobiological lessons for the ESA astronaut training program. What is the most challenging part of teaching an astronaut who might be an engineer or a pilot or a systems engineer and helping them to think like a field geologist?
Yeah, that's very important and challenging aspects because, as you say, they do not have the geology background, right? So you can't teach geology the way you would teach geology student, for example. But what is the success of such a training is that you have to focus on fundamentals and making it very practical. So I think the most important part of the training was hands-on field exercises where astronauts learn how to observe rocks, how to describe geological features. They were trained, their brain, what they're looking for. So some proxies again in the rocks, and how to communicate those findings back to scientists on Earth. And that's really the key skill for planetary exploration. It's not turning astronauts into professional geologists overnight, but teaching them how to make the right scientific observations and how to work efficiently together with the science team on the ground to identify the most optimal samples to bring back, because this is exactly how the exploration for them looks like. They do make independent observations, but then decision is a teamwork. It's backed up by mission control on Earth. So we teach them how to work with geologists in the most optimal way.
Excellent, Gabriela. Now, we are suckers for science here. So let's pivot over to your recent paper on Noachian FEMG phyllosilicates. Now, before anyone thinks this podcast episode is going to zoom into orbit over everyone's head, would we be right in saying that Noachian iron magnesium phyllosilicates just means ancient or old clay, a very specific ancient clay, or solidified mud that's 4 billion years old, just a little bit older than your muddle-headed host here? Tell
Mm.
us a little about these phyllosilicates, please, Gabriela.
All right. So look, we know the mineralogical signature is iron magnesium phyllosilicates, which I have explained before. It formed very late in the Martian history, where Mars was habitable. So we want to access that window to Mars with these clays, investigating them, because yes, they also have a high potential to trap the biomolecules in the structure and preserve them over the long period of time. But what we know about them is what you just basically mentioned, that it's iron magnesium phyllosilicate, and we know it from the spectroscopic orbital data. Of course, there are many variations. There are saponite, nontronite. Some of them are, for example, pure. So we see two different types. One of them are pure iron magnesium phyllosilicates with the lower bedrock group in Oxia Planum, so older. And the other type is also iron magnesium phyllosilicates with some mix of other minerals in them. Anyway, we know about the mineralogical signatures, but about the rock itself, we don't know. Of course, what comes and crosses our mind is the mud, but we don't know what is actually hosting these mineralogical signatures. We don't know what kind of rocks we are expecting to find on the surface. And that's the biggest also challenge for us, for science planners, to imagine how the surface would look like. Because these iron magnesium phyllosilicates, they can be hosted in a very fine-grained mud-like rocks, so very soft, and that would be ideal for us, especially for drilling and preservation of the biosignatures. But also they can be hosted in the basaltic rocks, so they could be leached from the basaltic material and just accumulated on the surface through the hydrothermal activity. So there are many ways how they could look like, and that's one of the mystery that we can only solve with the in situ observations. And that's why we need some ground samples as well, because the orbital observations, they have certain limits and they can give us certain amount of information. but to confirm the host rock and mineralogy as well, because we know they are iron magnesium phyllosilicates, but for example, they can have the mixture of any other interesting minerals like carbonates of hydrated silica that we cannot resolve from orbit itself. So we can only go and do the ground truth spectroscopic analysis with the instruments on site to find out what are the other minor mineralogical phases that are also preserved within these rocks.
Fantastic. I'm looking forward to this mission so much. And
Okay,
has it
thank
got
you.
has it got two names? It's the ExoMars rover, and it's also called the Rosalind Franklin rover.
Okay, so it's ExoMars mission. It calls ExoMars mission, but ExoMars Rosalind Franklin rover. It's a rover. It's like Mars 2020 is a mission in the US, but Perseverance rover is the rover that takes part in the mission.
Beautiful. Thanks, Gabriela. Now, that leads on to another aspect. Let's move from the moon back to Mars, where we began today. We know that a lot of our listeners are non-geologists. For those of us that are not familiar with the topography of Mars as well, where is Oxia Planum? What is Oxia Planum and where is it?
Okay, so Oxia Planum is an interesting terrain located near the Martian equator, and it's between transition of ancient southern highlands and northern lowlands of Mars. Why is it so attractive for the science? Let's speak maybe about science, not about the operational constraint. Is that, as I mentioned, it has a vast exposure of these iron magnesium clay phyllosilicates. They covered 80% of the landing ellipse, so the likelihood of landing of them is extremely high. What is also important with Oxia is that it has one of the oldest terrain on Mars. So in the past landing sites with the other rovers, we investigated craters and so on, but this time we will access the most ancient rocks, which were formed over 4 billion years ago, where we know that water was on the surface of Mars. So when the conditions were much more habitable than they are right now. So it has these clays, and they are very important for the exploration because they do not only form in the presence of water, but they also act like sponges for the biomolecules. So they are capable of trapping the biomolecules into their structure and preserving them over the long period of time. On top of that, Oxia is very interesting because there are also from the orbit we have some observations that show ancient channels, sedimentary deposits, delta and river beds that are also potential habitable niches for the life. So yeah, it is very ancient terrain, and it has the most ancient rocks that we will ever access so far with the rover, and therefore increase the likelihood of finding life.
Excellent. I think we should all go to Oxia Planum. Thank you, Gab. And
Sign me in.
if there's any sci-fi fans listening right now, go and watch the original Total Recall. It's a classic Mars adventure. But coming back to reality, you've spent time on SDEC Open Day panels discussing things like Martian invasions with legends like Jeff Wayne. Do you feel that being a great scientist today also means being a great storyteller? And what does that marketing background of yours, how does it act as a secret weapon when you've got an audience in front of you and you're turning complex geochemistry into stories that actually fire up and fire people's imaginations?
Okay, so I think that being a scientist is not just about doing great research, but also it's about being able to communicate why that research matters with the wider audience. So space exploration is ultimately funded and supported by society. So if we cannot explain our work in the way that inspires people, we are missing a huge part of our mission of exploration and inspiring the next generation. And I think, yes, probably some of my past marketing experiences helped a little bit in that mission to communicate science to wider audience, because it taught me how to translate very complex scientific concepts into stories that people can emotionally connect with.
Yep.
Whether that's imagining what are these Martian clays, how the astronaut geology training works, or like how to find search of life on Mars. I always try to make a little story about it so people can visualize in their heads before the going deeper into the science and the details.
Beautiful. Thank you. And you're doing exactly that. I'd love to look at the bleeding edge of your work now. Perhaps the Arise project or the ExoMars 2028 preparations that you have to do. But what is the one technical hurdle that keeps you up at night, that worries you? And what is the discovery that makes you want to get to the lab every morning?
There are, of course, many challenges, but I think the biggest challenge in my daily life and my research, either it's in the lab or working with the scientists, is how to make the science operational on the planetary surfaces. We have a lot of questions back here on Earth, and everyone, it's very interdisciplinary project. Everyone has their priorities, opinions. But I think the biggest challenge is how to make a common vision for the team to follow and prioritize the mission objectives. Because, right, we want to investigate everything. It's amazing area. It's a new area where we land. So we want to check all of the boxes sometimes, and we are distracted by, let's say, great volcanic feature, but is it really a priority for the mission? It's not, right? We are looking for the life. So the challenge is to how we prioritize our goals and targets in the exploration. And also the operational aspects of it. I think it's the biggest challenge because on Mars, every measurement costs time, energy, and data volume. So we can't just repeat observation endlessly the way we would do it in laboratory on Earth. And also mistakes are incredibly expensive. So yes, a huge part, I think, and challenge of this is like we have limited resources, but we have to do meaningful science. So this is what I'm trying to figure out, how to collect meaningful data, science data with the minimum information we have, something that we absolutely do not face, the problem we do not face here on Earth, but we have it on Mars, for example.
Wow, so many difficult decisions, but it sounds like you've got some wonderful teams to work there. Now, there were many rover missions already on Mars. We've had some beautiful rovers up there. Sojourner, Spirit, Opportunity, Curiosity, Perseverance, and Zhurong. How is the ExoMars rover, how is it different, and why do you think that you will find life on Mars?
Okay, so indeed, ExoMars rover is much different to what we currently see on Mars and what we have seen in the past. So the first, I think the biggest advantage is that we have a drill that can reach down to 2 meters depth. So for the first time, we'll access the subsurface of Mars. So the deepest we have went so far was just 17 centimeters depth with Viking missions in 76. And this time we will get samples with 2 meters depth. And that is important because, as you know, there is radiation on the surface of Mars. So we have a hostile environment with a lot of radiation and also perchlorate salts in the soil of in the regolith of Mars that basically can destroy the biomolecules, the very sensitive biomolecules that could be preserved. I think, and everybody in the community agrees, it's very unlikely to find them on the surface. And many studies, they show that if you go under the surface, the likelihood of preserving biomolecules increases. And also, they are stored on the surface in minus 60 degrees Celsius. So they have much better state of chemical preservations than anything that we previously analyzed. Also, what is important, we have very sophisticated mass spectrometry system on ExoMars Rosalind Franklin rover. So we have a mass spectrometer that calls MOMA, Mass Organic Molecule Analyzer, that it's able to investigate for the first time on Mars samples on the biomolecular level. And also, it's the first time that we will do tandem mass spectrometry. So the same exact grain of interest, if we find something potentially biotic, will be double checked by 3 different instruments to find out whether or not this biogenic signal is confirmed by multiple instruments and give us the final answer whether or not this could be created by life, whether this rock or sample has this biomarker inside it.
Beautiful. So exciting. I can't imagine what the anticipation would be like waiting for data to come down from your core samples and doing your drilling. Look, Gabriela, we've definitely gone full science today, and it's been a blast, but I know our listeners would, like me, love to know a bit about this person behind the missions a little better. Science is basically beautiful stuff, but it's done by humans, by people. So when you aren't calculating rover paths or looking for signs of life on planets, how do you like to spend your time when you're not at the lab? What's something completely non-scientific that keeps you smiling?
Um, I think I still have explorer spirit. It still stayed with me. As I mentioned before, I dreamt to explore the world. So it's still very close to my heart. So I love exploring. So traveling is still a big part of my life. I try to travel as much as possible. I'm interested in both different cultures. I like to travel to countries with, for example, totally different religion and culture to just put things into perspective, like how diverse we are and how different life can be on Earth as well. But also, I really enjoy doing some activities such as cycling, climbing, hiking as well. So I like being active and be surrounded by nature. Yeah, and just being present and enjoying my life and trying to appreciate the very simple things as well, than just thinking about the big ideas like exploring space. I feel like there is so much to be explored here on our planet as well, and I just love doing it.
Fantastic. And that keeps you very much alive. So here we are. Finally, the microphone is all yours, and you have the opportunity now to give us your favourite rant or rave about one of the challenges that we face as humans, whether it's the role of AI in mineral identification or the importance of diversity and international collaboration in space. You've hinted at that, or even our human quest for new knowledge, or perhaps what are you most passionate about right now? The microphone, Gabriela, is all yours.
Thank you. I think that's also a very interesting question. But I think like one of the challenges that we are facing today as scientists, for example, let's speak from my point of view, is to help to understand people why are we actually doing space exploration and why it matters. Right? There are a lot of people who are still questioning, why do we have to do it? We have so many problems here on Earth that we have to solve. But many people basically see it as something distant and futuristic that we cannot relate to on a daily basis. But I think we don't know, or people don't know, how actually space technologies affect our every single day. We are using the instruments and tools such as GPS navigation, weather forecasting. We have satellites to monitor the climate and natural disasters. And we are getting ready to use this technology to better respond to, for example, disasters that are happening on Earth. So we have to communicate it with people that we need to invest in this space technologies so we can also benefit here on Earth. And what is, I think, very fascinating, that humanity invests very little into space comparing to the impact it also has. So on average, I think it's 0.3% of the budget of each country, how much we put into space exploration, which is much smaller than some people can imagine. So I think the biggest challenges is the communication and helping people to understand that investing in science and exploration is not a luxury, but it's rather an investment in technologies, innovation, and education that then help us to evolve and help to sustain our future here on Earth. And I would like us to communicate more about it and the importance of what we are doing.
Exactly. Thank you so much. Yes. And in return, for every dollar we spend in space, we get $7 back. So there are huge benefits to it.
Absolutely.
Thank you, Gabriela. Oh, look, one last thing. What are you keeping your eye on? What should we look out for in the near future?
I think the future is getting excited. And for example, I work at a space agency, but I think we should have an eye on looking at growing role of the private industry in space and how we can work together to make programs and missions much faster with our commercial partners. So as you know, we are seeing incredibly rapid process with reusable rockets, private lunar landers, private robotic missions, and commercial missions to Moon and Mars. So I think the next decade could completely redefine how we explore space. So I think let's look forward to see governments and private companies work together much more closely, and let's bring the science fiction, thanks to that, to reality much sooner than we would do in a traditional way.
Beautiful. Excellent. Keep looking up. Well, thanks, Dr. Gabriela Ligeza. From the mineral labs of Zurich to the surface of Mars and the moon, it's been an absolute thrill to trace your journey, and your work is literally paving the way for the next generation of explorers. Thank you so much for joining us on Astrophiz.
Thank you very much, Brendan. It was an absolute pleasure, and congratulations on your podcast anniversary. And thank you very much for communicating science to the wider audience. I think this is exactly what we all need to do. So I'm looking forward to follow up your future podcasts as well. And thank you for having me.
So make sure you join us for another special 10-year anniversary episode on the 1st of June. Dr. Ian Astroblog Musgrave first joined Astrophiz in June 2016, and since then he has given astrophotographers naked eye, binocular and telescopic observers his monthly sky guide on what amazing things you can look for in your local skies. Thanks, Ian. Twice a month, Astrophiz has featured an incredible diverse lineup of experts spanning the entire spectrum of space science, engineering and data analysis. Rather than sticking to a single niche, my interviews dive deep into both the theoretical side of understanding the cosmos and the practical, hard engineering side of capturing cosmic data so that we can understand our own universe. Make sure you're subscribed to Astrophiz so you're the first to hear it. And remember, Astrophiz is free, ad-free and unsponsored. Keep looking up. Clear skies.
Radio Wave!